Hi everyone, welcome back. In this video, I'm going to show a generic analysis of an Igmf active filter or infinite gain multi-feedback active filter circuit. All right, so it's a circuit on the left here, and I'm calling it generic because I'm basically replacing all resistive or capacitor components by this generic terminology of Z. All right, so Z1 all the way to Z5. That's impedance 1, impedance 2, all the way to impedance 5. So in other words, the location of these generic impedances can be replaced by either a resistor or a capacitor. In a different video, I will show you guys how to then analyze a low pass or a high pass or a band pass filter implementation of this circuit. All right. So as usual, the first thing we need to do is obviously label all the currents and voltages that are involved. So the first one I want to put, I think, is this node here. This node in the middle here is not really connected to VO. It's not connected to VO. It's not connected to VI. It's not connected to ground. So it's by itself. So I'm going to call that Vx. So I'm going to put Vx here. All right. So that's my Vx. That's my Vx node. Let me just make that a bit. All right. Okay. So that's my Vx node. So that's this node in the middle there between these four impedance components. All right. Next, I'll label the feedback current IF that's flowing from VO towards back towards the circuit. Oh, by the way, it's multiple feedback because of, as you can see there, the IF is fed back via two feedback paths through Z4 or Z4 and Z5. All right. I'll continue labeling the current that's flowing through Z5 there as I5. So I'm going to call that I5. Okay. And if you notice, I5, based on the assumption, because we're analyzing a negative feedback op-amp, so the two assumptions that you guys should remember always will apply. So for example, the I5 here, when it comes down, it does not enter the non-inverting terminal. Sorry, the inverting terminal. It doesn't enter the inverting terminal, but instead goes completely through Z3. All right, so that means the I5 current actually completely also goes through Z3. All right, so there's none going into the inverting terminal. All right, so let me just label the current I4 into Z4. So that's going to be I4 here. All right. Okay, so the idea is you have that current I5 coming in, sorry, IF coming in, and it gets split into I4 and I5 through these two components. All right, next I'll label this the current going through Z1 as I1, so that's going to be I1 flowing through Z1, and then finally the current through Z2 I'm going to call it obviously I2. Okay, so now I think pretty much have all the current. So I have a voltage node here called Vx, and I have a bunch of current labels. By the way, you can make this arrow go whichever way you like, as long as based on those arrows you construct the right kind of KCL, KVL, Ohm's law equation. All right, that's really important. Okay, because once you put down your arrows and you derive the correct set of equations, you always receive, or you always end up with the same answers. All right. Now the other thing I want to put down is this. If you notice here, the non-inverting terminal is actually tied to ground, and based on the second assumption for ideal op-amp with negative feedback, then even the inverting terminal will also be at 0 volts. All right, so I'm going to put a 0 volts there just to remind everyone. That's that node over there. All right, just well, basically the inverting node. So this is the inverting node that's at 0 volts because the non-inverting node is tied to ground. All right, so based on that second assumption. Okay, so I think we pretty much have all the labels in. So we can, well, let's just write some equations now. So the first one I want to write is, well, there are many equations I can write, but the first one I want to write is about this node at Vx here. If you notice, the current I4 flows into that node, I5 flows into that node, but I1 and I2 flows out of the node. So I can write KCL equation at Vx, all right? At Vx, all right, is going to be, okay, so it's going to be I4 plus I5 is going to be equal to I1 plus I2. All right, so that's our first equation in terms of what we can see in the circuit here. Okay. So next, I think we can straight away, set up what I4, what each one of these are in terms of the components, right? In terms of Ohm's law. So let's do that next. Currents here from Ohm's law. So we're gonna write basically an equation for each one of these: I4, I5, I1, and I2. Let's start with I1. So what is I1 equal to? Well, if you look at I1 is this current here. So obviously it's going to be Vx minus Vi divided by Z1, right? So that's just Ohm's law. So Vx minus Vi all divided by Z1. All right, so that's our first equation. So next equation, I can write about I2. So what about I2? Well, I2, if you look at I2, which is here, is Vx minus 0, because it's Vx, that's this node here, minus 0, because the current direction is going down, so that's Vx minus 0 divided by Z2. So Vx minus 0 is just Vx, right? So Vx divided by Z2. Okay, so that's our I2. Next, let's write about I3. So what can I say about I3? Well, this is I3. I3 is, oh, sorry, I don't have I3 because Z3 is basically I5, so let me do I4. So what is I4? Well, I4 is here, that's Z4. So that's this node here, which is V0, right? VO, sorry. So this is VO minus Vx over Z4. That's, again, just Ohm's law. So it's VO minus Vx. So it's going to be VO minus Vx divided by Z4. And then finally an I5. So I5. Okay, I5, actually there are, I can write two equations. If you notice here, I can write in terms of Z5 because I5 goes through Z5. Or I can write it in terms of Z3 because I5 also goes through Z3. All right. So I'm gonna use Z3. You can use Z5 if you want. The end result will still be the same. So I'm gonna use Z3. So I5 therefore is, well, okay, I5 is flowing here. So going through Z3. So we're talking about 0 volts. So this node here is 0 volts because of the reason I mentioned earlier. Minus Vx, so 0 minus Vx over Z3. So 0 minus Vx is just negative Vx, right? So negative Vx divided by Z3. All right, so negative Vx over Z3. So now I have all four results, if you like. Okay. Now, as our previous analysis on the Salem key, we need to figure out how to replace Vx with something that is in terms of components that we know. All right. The one that I'm going to use is something that's related to the fact that these two I5s, or the same I5, actually flow through to two different components. All right. So three different components. So I could equate the I5 of going through Z5 to equal to the I5 that is going through Z3. All right. So here I'm going to write to discover, if you like, Vx. All right. We notice that I5 goes through two different components. All right. So I'll say what they are. That's Z3 and Z5 and Z5. All right. So that's basically we can see I5 flowing through both. So I can say that the current across Z3 is the same as the current across Z5. So I can write. So what is the current across I5? I5, I equals V over R. So V over R here is, of course, 0 minus Vx over Z3, right? So I5 going through Z3 is 0 minus Vx over Z3, right? So I'm going to have so one side of the I5, which is Z3. Okay, so I'm going to write negative Vx divided by Z3. Oops. All right, is going to be equal to I5 that is going through Z5. All right, so now the I5 going through Z5 is just VO minus 0, right? So VO over Z5. So it's going to be VO divided by Z5. Okay. Okay, so now I have an equation that basically has I can turn this around and therefore get an answer for Vx, right? Vx is going to be equal to, all right, so therefore, so I'm going to say dot here and then going to continue. Therefore, Vx is going to be equal to, well, just do a bit of manipulation here. Z3 is going to go to the other side, and a net negative can put to the other side. So it's going to be negative VO, all right, and then it's going to be Z3 over Z5, all right. That's it. So that's what our Vx is going to be. Okay. All right. So now we have an expression for all the currents that we discovered at the node Vx, and also we figured out an equation to replace Vx. So the next thing is just obviously to just put everything together to satisfy this KCL equation. So we start with I4. So I4 is just this one here. So first I'm just write all that down, right? So then I'll say here replacing all right, so this is going to be I4, so that's I4, plus I5. I5 is this guy over here, so that's plus I5, is equal to that's all. Okay, I1. I1 is this guy here. Plus I2. I2 is just Vx over Z2. All right. So that's our equation. Our KCL equation now being substitute with all these I expressions, if you like, to become this. All right. So then the next thing we do is to replace all the Vx's with this term. All right. So let me just copy this. And then I'll say replacing Vx into the equation above. So first of all, let me just put everything in, and then basically wherever there's a Vx, I'm going to replace it with this term here. Okay. All right, so I'm gonna put in brackets. All right, that's that, and then you have this Vx as well in brackets. And then this term in brackets. And then this term in brackets. Okay. So next thing is obviously just to expand this. All right, so expanding above. So what are we gonna get? I'm just gonna copy this down again. Okay. All right. So here, so you have a VO minus minus. So obviously it means VO plus, and then VO times this. So I think I'll expanding and factorizing. So I'm doing factorizing. All right. So this is going to be, like I said, this is going to be VO plus, and then VO Z3 over Z5. So I can take VO out. So I can just factorize that out. So I'm going to put a bracket there. It becomes 1 plus, and then it's going to be this term here, right? 1 plus that term. Okay. So let me just 1 plus that term. All right. So then get rid of all this other stuff. Right. All right. So it's going to be 1 plus. Okay, that's done. Next, well, this thing is just going to be a positive VO. Next one, right? So the next one is just going to be positive VO. All this times all that. Okay. And the next one is, okay, so this one is, okay, in this one, I think what I'm going to do, I'm going to split this term, that's this whole thing here over Z1, and also this term VI over Z1. So then I'll have two expressions here. So this negative is still there. All right, so I'm going to put it over here. It's a new thing. All right, and that's going to be over Z1. So Z1 is going to end up down here. Z1 1. All right, so that's the first term is going to be like, and then it's a minus VI over. All right, so it's going to be minus. So minus VI over Z1. All right. So that's just this term here, this part here being split into two, both divided by Z1. All right. Okay. So next is this term here. Well, that one simply, well, basically Z2 ends up on, with Z5 there. All right. So it's going to be just simply Z2 down there. All right. And the whole thing is just going to be a minus all of this term here, right? Just get rid of all that and just rewrite this part. So it's going to be minus and then that term. All right, so Z2, Z2, Z5 down there. This one is Z1, Z5 there. All right. Okay, so I can actually do the same over here as well. I'll expand this side as well. All right. So then becomes VO over Z4, right? Because basically I'm dividing Z4 for both. Okay, actually I'll do this. I mean, this basically is VO plus all this. So it's going to be VO over Z4 plus all of this over Z4, right? So let me just make it a little simpler here. So the first term on the left is going to be VO divided by Z4. Okay. All right, and then plus, all right, so plus what? Well, actually it's going to be this term here, right? It's going to be this term here. So I'm going to get rid of all of this, and then, and then it's going to be Z4 down here as well. So Z4. All right, so basically what I've done there is I've split these two terms into their own over Z4 expression. So you have a VO over Z4, and then a plus VO Z3 over Z4 Z5. All right. Okay. Then I think okay, and this one also I'll just simplify it straight away. So the whole all of that becomes divided by Z3 as well. So therefore it's going to be Z3 at the bottom, and then you should notice that Z3 will cancel out with the top Z3, right? So it's going to cancel out. All right, so Z3 and Z3 will cancel out, so I might as well do it here. So I'll just straight away becomes 1 over, all right, 1 over Z5, okay? Okay, so now I have an expression that where all the VOs have been split. VI is also by itself, so I can actually combine VO all on one side and VI on the other side. All right. So I'll just say collecting terms. So what I'll have is I'll have a VO on the left side, and I'm gonna keep VI on the right. So I'll have this, these guys are fine. So I need to bring these guys across to the other side as well. So it's going to be just, obviously, just this. When it goes to the other side, it becomes a plus. All right. And so is this. All right. When it goes to the other side, it just becomes a plus. Okay. All right. So next I'll just factorize VO out. Just take VO out of all of these terms. Okay. I'll just take VO out of all these terms. So factorizing. Okay, so I'm going to have a VO on the outside. So my VO is going to be on the outside. Sorry, not V0. VO. Right, VO is on the outside is equal. And multiply by. All right, so there's a whole bunch of stuff here. So for example, this is going to be 1 over Z4. This one is just going to be Z3, and then that term there. This one's just going to be 1 over Z5. The next term here. So 1 over Z5. So 1 over Z5. Okay, and then this part is just going to be that term there, and this part is just going to be that as well, just that term over there. All right, so all of this. Yes. All right. Okay. So the next thing I can do is I can, if I were to divide every term by Z3, just to get rid of the Z3 at the top there. All right. So let me do that next. So if I say divide by Z3, all terms by Z3. I just want to remove that Z3 term at the top there, right? So then my equation now is going to be a little bit simpler. So if you divide, so this one is divided by Z3. That means I'm going to get a Z3 term at the bottom there. All right, and then this part is just the Z3 term will disappear at the top, so it becomes 1 over Z4 Z5. All right, 1 over Z4 Z5. All right, this one is just going to be 1 over Z3 Z5 once I divide by Z3. All right, and this one again is just going to be the Z3 will just disappear, so just be 1 over Z1 Z5. Okay, and this one again is just going to be 1 over Z2 Z5. Right, so the top term there will just disappear. right? So, and of course, on the other side, there's going to be a Z1 times Z3 at the bottom here. Okay, so once you do, so this is what you get after you divide everything by Z3. Okay. So the next thing we can do is, well, if you notice, there's the Z5 pretty much in quite a few places there, so I can factorize that out. All right, so I'm going to factorize that out. So that's going to be, so we just copy that, and I say factorizing the internal bracket. Okay, so if you notice here, so Z5 terms are in all of these, right? So this is 1 over Z4, Z5, Z3, Z5, Z1, Z5. So I can actually have a 1 over Z5, all right? And into, I'm going to arrange it in numerical order. So this is going to be like Z1, right? And then 1 over Z2, 1 over Z3, and finally 1 over Z4. All right. Okay, so the next thing to do is, of course, to combine V over Vi, i.e. H of S, into a final expression. All right, so let me just make some space here. Just take this up and put it over here at the top there. Okay. All right, so then so that term is now going to be equal to negative, all right, and the top part is going to be 1 over Z1 Z3. Okay, all of that is going to be divided by all of these terms here. All right, so this is now the final expression for the generic Igmf active filter, where all the components are represented by impedances Z1 to Z5. So in another video, I'm going to show how to convert this into a, either a low pass, band pass, high pass, etc., by simply replacing these components by either resistors or capacitors. All right, so this is quite a flexible circuit for building, especially band pass with just a single op amp. So it's usually used to represent a band pass filter. All right, so thanks for watching. See you guys next time.